We have a new image captured by researcher Keng Zhang from Lowell Observatory in Arizona. He used a 152mm Ritchie-Chrétien telescope to record the comet on November 2nd. It's worth noting that 3I, Atlas, is now appearing in the morning, even under non-ideal observation conditions. But at the forefront of this narrative is another image that has raised a red flag, a capture made by the Mars Reconnaissance Orbiter when Atlas crossed near Mars's orbit on October 3rd, 2025, at about 27 million kilometers from the planet. Reports indicate that the data was obtained between October 2nd and 3rd, and that part of this material has been locked or inaccessible since then, which immediately raises questions about transparency and scientific priority. This would indeed be the highest quality photo we humans have. The retention or delay in releasing this data only amplifies the nervousness among scientists and lawmakers. This is data that could guide the next observations before Atlas leaves our system. The public episode took a disconcerting tone. NASA replied on Twitter to Kim Kardashian's question about Atlas with a short, reassuring message. No aliens, no threat. While formal requests from scientists and congressional offices asking for the high-resolution images appear to have received little or no response. That contrast between rapid media-facing communication and a bottleneck in the scientific data stream creates an informational vacuum. When a scientific agency engages a high-reach channel and simultaneously delays sharing crucial data with researchers, it opens space for rumors and public speculation. That mismatch undermines public trust and slows the independent verification that is the backbone of science. The unrestricted release of the high-rise camera data from the Mars orbiter is urgent for rigorous analysis. A recent public remark by Elon Musk reignited the debate. He noted that some natural bodies can be rich in iron and nickel. That observation is relevant, but omits a crucial detail that Atlas's data seem to show. The nickel proportion appears to be far higher than the iron, a composition that departs from known metallic asteroids. This raises two important implications that must be made explicit. First, nickel, in such high purity and in such a high ratio to iron, rarely appears naturally without substantial accompanying iron. Separating nickel from iron on a large scale requires metallurgical processing and industrial techniques. Practically speaking, producing nickel-rich alloys with low iron content involves refining steps, electrolysis, chemical separation, high-temperature metallurgy, not found spontaneously in the cosmic environment. Second, the unusually metal-rich composition casts doubt on the object's age and origin. Heavy elements like iron and nickel were not abundant in the early universe. They are forged inside massive stars and dispersed by supernovae. Therefore, a high metal content generally signals later stellar generations. In other words, material that is, by cosmic standards, younger. So, if Atlas is extraordinarily rich in industrial-type metals, and especially in nickel separated from iron, two possibilities arise. Either it formed in a region or epoch of the cosmos where multiple generations of stars had already produced significant metals, making it younger than many classic interstellar objects, or some of its metal content was processed by a technological agent. In short, metal composition and refined metal purity raise both the hypothesis of relatively recent formation and the hypothesis of artificial processing, and both require careful investigation. The observed non-gravitational acceleration of Atlas demands rigorous physical explanations. If that acceleration were caused by cometary gas ejection, conservation of momentum implies the object would need to lose roughly 1/6 of its mass, an enormous amount. In practical terms, that would mean billions of tons evaporated over weeks, producing a debris cloud detectable by multiple instruments. So far, post-perihelion images have not revealed a massive cloud compatible with that scale of mass loss. That discrepancy between the physics-based calculation and observations is the reason scientists are asking whether we are seeing an unfamiliar natural process or something that might imply active propulsion. The scientific community has organized an intensive observation campaign. Atlas reaches its closest approach to Earth on the 19th of December 2025, and between late November and January, it will be under coordinated surveillance. This is the best chance to detect the hypothesized debris cloud, identify jets, confirm composition, and test competing hypotheses about its nature. Additionally, release and analysis of the images taken near Mars by the Mars Reconnaissance Orbiter are crucial. Those data could provide direct information on morphology, jets, and composition from a vantage point different from Earth-based telescopes. Science needs these data now uncompromised by politics. Before concluding, it is essential to summarize the anomalies that make Atlas singular. Each represents a fundamental departure from established comet physics that, when combined, creates a pattern unprecedented in our understanding of natural celestial objects. 1. Retrograde trajectory with ecliptic alignment. Atlas follows a retrograde orbit moving opposite to the direction of planetary motion around our star, yet maintains precise alignment within 5 degrees of the ecliptic plane. In typical interstellar encounters, objects arrive from random directions in three-dimensional space. The ecliptic plane represents less than 3% of possible approach angles, making this alignment statistically remarkable. Moreover, retrograde motion combined with ecliptic alignment suggests either extraordinary coincidence or intentional targeting of our planetary system's orbital plane. 2. Anti-solar jet phenomenon. Between July and August 2025, Atlas developed a prominent jet pointing directly toward our star, creating what astronomers term an anti-tail. This behavior fundamentally contradicts comet physics. As comets approach stellar bodies, solar radiation pressure and stellar wind push vaporized material away from the star, creating the characteristic tail pointing in the anti-solar direction. Atlas's sunward jet suggests either an unknown physical mechanism or active propulsion overcoming natural radiation pressure, a phenomenon never documented in any known comet across centuries of observation. 3. Extreme mass velocity characteristics. Atlas possesses a nucleus approximately 1 million times more massive than Oumuamua and 1,000 times more massive than Borisov, yet travels faster than both objects. In gravitational dynamics, more massive objects typically move slower when originating from similar distances due to energy conservation principles. This size-speed combination is analogous to observing a freight train overtaking sports cars physically possible, but requiring extraordinary initial conditions or additional energy sources. 4. Precision planetary encounter sequence. Atlas's trajectory brought it within close proximity to Mars, Venus, and Jupiter in a coordinated sequence, while timing its perihelion passage to occur during solar conjunction, rendering it unobservable from Earth precisely when closest to our star. This stealth approach required arrival timing accurate to within days across an interstellar journey spanning potentially thousands of years. Such precision resembles mission planning rather than random gravitational encounter. 5. Industrial metallurgy signatures. Spectroscopic analysis reveals Atlas contains nickel to iron ratios significantly higher than any known natural comet, resembling proportions found in terrestrial industrial alloys rather than primordial solar system materials. Natural comets typically reflect the metal abundances of their formation regions, with iron dominating over nickel by substantial margin. Additionally, Atlas exhibits only 4% water content by mass extraordinarily low, considering comets are fundamentally dirty snowballs composed primarily of water ice mixed with rocky debris. 6. Unprecedented optical polarization. Atlas demonstrates extreme negative polarization of reflected light, a property describing how electromagnetic waves orient after reflection from the object's surface. This polarization signature has never been observed in any other comet, including Borisov, which displayed typical comet polarization characteristics. Negative polarization of this magnitude suggests surface materials or structures fundamentally different from known natural cosmic bodies, potentially indicating artificial surfaces or exotic material composition. 7. Wow! Signal directional convergence. Atlas originated from a sky region within 9 degrees of the famous 1977. Wow! Radio signal, a 72-second transmission detected by SETI that remains the strongest candidate for extraterrestrial communication. While 9 degrees represents a relatively large angular separation, the coincidence becomes statistically significant when considering the signal's unique characteristics and Atlas's other anomalies. This directional correlation adds another layer to an already improbable pattern. 8. Anomalous photometric evolution. Near perihelion, Atlas exhibited brightening behavior exceeding any known comet, while simultaneously becoming bluer than our star itself. Typical comets brighten due to increased sublimation of ices as they approach stellar heat sources, but their color remains relatively constant or shifts toward redder wavelengths due to dust production. Atlas's blue shift suggests either unusual surface materials or energy emission mechanisms inconsistent with standard comet behavior under stellar heating. 9. The mass loss acceleration paradox. ALMA radio telescope observations detected non-gravitational acceleration, indicating Atlas should have lost at least 15% of its total mass, over 5 billion tons of material, to account for the observed trajectory deviation. Such massive outgassing would create an enormous, easily detectable debris, cloud, or coma extending millions of kilometers around the object. However, no such cloud has been observed despite intensive monitoring. This presents a fundamental physics problem. Atlas displays acceleration typically associated with massive material loss while showing no evidence of the required mass ejection. Science advances on the basis of data, and data must flow freely among researchers. Transparency and rapid sharing are crucial, so we can rigorously answer the question, are we observing an unknown natural phenomenon or something far more unsettling? We began with a leaked image in Mars orbit and arrived at a scientific crossroads. Atlas accumulates properties that challenge conventional explanations, from counterintuitive jets to a metal-rich composition that may require industrial processing and that calls its cosmic age into question. Recent public interactions from NASA answering high-profile media figures to technical comments by personalities like Elon Musk only underscore the urgency of unfettered access to the data, especially those captured by the Mars Reconnaissance Orbiter. In the coming weeks, we will learn whether Atlas can be explained by a debris cloud or whether we must reconsider fundamental assumptions. Science is ready for the truth, provided the data circulate openly. Comment and share your questions. Follow closely. The outcome could redefine what we know about interstellar visitors.